Hello my friends and welcome back to the You Can Do TV channel. In the world of ultra-large ocean-going ships, the crankshaft isn't just a part. It's the rotating backbone that turns fuel into forward motion, hour after hour, mid-ocean, with no second chances. At this scale, it can rival a bus in length and tip the scales like a loaded rail car, yet it must run with watchmaker precision inside a brutal engine room. That's why these giants begin in extreme foundry work, where molten steel is poured and refined, then move into heavy open-die forging, where thousands of tons of controlled force densify the core and shape the future journals. Finally, heavy-duty turning and machining carve every surface into alignment, down to microscopic accuracy. In this video, we'll walk through the key stages that transform raw steel into a truly colossal marine crankshaft, built to keep a floating city moving across the planet. Open-die forging is the process that gives marine crankshafts their deep, internal toughness. Unlike closed dies that stamp a final shape, open dies work more like a disciplined choreography. The hot steel is compressed in steps, rotated, reheated, and compressed again. The goal is to refine grain flow, close internal porosity, and push sound metal toward the core, exactly where a crankshaft must survive years of torsion, bending, and shock loads from slow-speed propulsion. Technology makes that control possible. It starts in the furnace, where massive ingots are soaked until temperature is uniform, typically around 2000-2, 300 degrees Fahrenheit, 100 to 260 degrees Celsius, for forging. Hot enough to let steel deform without cracking, but not so hot that it loses structure. Then comes the heavy machinery, open-die hydraulic presses and manipulators that turn a multi-story tall workpiece with millimeter-level intent. Modern presses deliver thousands to tens of thousands of tons of force, but the real breakthrough is repeatability. Sensors track ram position, pressure, and stroke timing. Operators monitor deformation per pass. Automation helps keep each reduction consistent across the shaft's length. That's how a forge can move metal inside the workpiece, stretching, upsetting, and drawing sections so the journals and webs can later be machined precisely. Manipulators and cranes are just as critical as the press itself. A giant crank blank can't be handled like a smaller forging. It must be supported to prevent sag and unwanted strain while it's hot and semi-plastic. Computer-assisted handling systems coordinate rotation and feed rate under the press, so every bite lands where it should. Because one uneven reduction can introduce residual stress that shows up months later as distortion during machining. Quality technology closes the loop. Between heats, the forging is checked with ultrasonic testing to find subsurface flaws. And after heat treatment, it's verified again. Because a marine crankshaft isn't judged by what you can see. It's judged by what isn't hiding inside. Final machining and metrology bring the part into alignment, often holding critical geometry to thousandths of an inch, hundredths of a millimeter, despite the scale. Finally, the human factor remains central. Skilled crews interpret the press feel, thermal behavior, and inspection signals, while safety standards, especially in heavy lifting, hot work, and pinch point zones, reflect an OSHA-style discipline, where procedure matters as much as horsepower. In the end, open-die forging technology doesn't just make a crankshaft large. It makes it reliable, a component engineered to turn quietly for decades, deep in the engine room, carrying the torque that moves global trade across the sea. After forging has done its job, locking strength into the crankshaft's core, the next battle is precision. A marine crankshaft for an ultra-large vessel doesn't just need to be strong. It needs to be straight, balanced, and dimensionally perfect across a part so long and heavy it wants to bend under its own weight. This is where heavy-duty CNC turning and machining becomes the quiet hero of the build. In a modern crankshaft bay, the centerpiece is a giant CNC lathe or turning milling center designed for extreme loads. The machine's bed, headstock, and bearings are engineered like a bridge, rigid enough to resist vibration, stable enough to hold geometry for hours, and powerful enough to cut high-strength steel without shatter. The workpiece is supported by multiple steady rests and tailstocks along its length, because at this scale, the difference between perfect and scrap can start as a tiny sag. CNC control matters because marine crankshafts are not simple cylinders. They're a sequence of main journals, crank pins, fillets, and webs, each one positioned to translate piston force into smooth rotation. Heavy CNC systems coordinate spindle torque, tool pressure, and feed rate, so the machine removes material consistently, even as cutting forces change from one section to the next. High-powered drives deliver steady torque at low RPM, while adaptive control keeps the cut stable, protecting surface integrity and tool life. Metrology is integrated into the process, not saved for the end. Large crankshaft lines use in-process probing, laser measurement, and temperature compensation to account for thermal growth, because even a few degrees of heat in the steel or the machine can shift readings on a part this large. After roughing passes, operators verify straightness and run out, then move into finishing cuts that bring journals into final tolerance and surface finish. In marine service, that finish is everything. It supports the oil film that prevents metal-to-metal contact at sea, under continuous load. Technology also protects the part from hidden failures. CNC programs manage toolpaths to avoid stress risers, especially around fillets where cracks love to start. Controlled radii, smooth transitions, and carefully sequenced cuts reduce residual stresses and preserve the forged grain benefits. And because a crankshaft is a rotating mass, machining is tied to balance. Material removal is planned with the final dynamic behavior in mind, not just the geometry. The human factor stays in the loop, but the machines extend human capability. Skilled machinists and engineers interpret sensor feedback, vibration signatures, and dimensional trends, making small corrections that prevent big problems downstream. In a facility built for shipbuilding, safety is part of the technology stack too. Guarding, interlocks, crane choreography, and strict procedures around pinch points and suspended loads reflect an OSHA-grade discipline where the scale demands respect. By the time the CNC cell is finished, the crankshaft is transformed again, from a forged giant into a precision marine component, aligned and refined to run for years in the heart of an engine room. It's the moment where brute force meets exactness, and where heavy machining turns raw power into reliable motion across the open ocean. Quantum of the Seas rises from Meyer Werft's building hall, each section a testament to coordinated engineering. Workers guide blocks into place with precision, assembling hull segments while robotic systems assist in alignment. It's remarkable how human skill and machines complement each other during block assembly. Cabins are fabricated in dedicated factories, then transported for installation, integrating electrical and plumbing systems seamlessly. The 3D virtual reality laboratory helps engineers visualize connections before they happen, reducing errors and delays. In the laser hall, components are measured and calibrated to exact tolerances, ensuring structural integrity. Final assembly sees cabins lifted into the ship, followed by detailed inspections. Departure from Meyer Werft is captured in a time-lapse sequence, marking the culmination of months of intricate construction. The coordination required to handle such massive blocks is fascinating. Even minor misalignment could cascade into major delays, yet the crew handles it smoothly. B-roll highlights the enormous scale, and you can't help but marvel at the complexity of shipbuilding.
The Gerald R. Ford aircraft carrier reaches a major milestone as its upper bow section is lifted into place. Engineers and crews coordinate cranes and hydraulic lifts to align the massive structure. Welders secure it to the hull, ensuring seamless integration. The operation highlights human skill, teamwork, and engineering at an extraordinary scale. The flight deck now spans 106 feet, equivalent to a 75-story building.
Powerful and precise. The Heister H22.00XM12EC empty container handler lifts up to 9,000 kilograms with a two-stage mast. Diesel engine roars to life, ready to stack containers effortlessly. As the spreader aligns with a 20 feet or 40 feet box, the side shift ensures accurate positioning. The cabin gives the operator excellent visibility to guide the lift. Hydraulic systems deliver the force needed for rapid stacking. It's pretty satisfying to see side clamps grip so reliably on each container. With oil-immersed disc brakes and a robust frame, this machine handles the hardest port work with confidence and stability.
Large casting projects begin with mold preparation. Mold preparation starts with sturdy frames. A sand-like material is poured in, flowing into every gap and surface. Layers are pressed down to form a compact block with strong edges. Once the mold is filled, the pattern is removed, leaving a cavity. Cores are added to define interior passages. The pace of the work feels steady and sure. Every movement shows coordination between people and tools. The mold gradually takes form with quiet power. Inox CVA constructs ultra-large LNG fuel tanks, 34 meters long and 6.6 meters high, holding 770 cubic meters of LNG. Each tank weighs 250 metric tons and requires careful handling from start to finish. The inner vessel, made of high-strength steel, undergoes hydrostatic testing with 800,000 liters of DM water. Welding uses advanced GTAW and GMAW processes approved by DNVGL experts. Outer jackets are stainless steel, with double-walled piping to prevent leaks. Vacuum insulation ensures LNG hold times exceeding 58 days. Tanks are then loaded onto trailers and shipped from India to the USA, requiring precise logistics coordination. Seeing these massive tanks move is unexpectedly thrilling. Engineers integrate pumps, valves, and instruments into the TCS housing. The design addresses extreme marine loads and operational challenges.
Giant beams tower above as the pioneering Spirit approaches the Ninian Northern Field. Ready to tackle one of the heaviest offshore jacket lifts ever, the 8 100-ton jacket is prepped meticulously. legs cut and lifting blocks attached with precision. Even the engineers seem a bit wide-eyed at the scale of this lift. Slowly, the JLS hoists the jacket from the seabed, tilts it on board, and secures it for transport. Skidding the structure onto the quayside, workers rely on concrete supports to stabilize it. The vessel's stability means no extra support barges are needed, cutting time and emissions. Hard to imagine an 85-meter steel giant moving almost effortlessly. Industry trust in all seas, engineering shines clearly. The teamwork and coordination here is next level. Hats off to the crew.
KTL Offshore transforms steel wire into the largest slings in the world. The facility begins with steel wire rope inventory, storing over 6,000 tons ready for heavy lifting projects. Slings up to 24 inches in diameter are prepared for specialized applications, including 2 McDermott 18-inch slings. It's impressive to see raw steel poised to support tremendous loads. The first Flemish eye is carefully formed by combining component ropes labeled A and B. Each loop and twist is aligned to distribute tension evenly, ensuring safety in operation. Observing how each element contributes to a larger system is fascinating. Finishing touches follow, with precise splicing and protective coatings applied. Workers inspect every sling, confirming strength and consistency. The scale of production inspires respect for human skill and engineering. Once complete, these slings are ready to serve offshore platforms worldwide, carrying enormous responsibility with unwavering reliability.
Heavy lifting on an FPSO integration project in Brazil reveals the sheer scale of engineering effort required to unite offshore modules into one floating unit. The atmosphere of the site feels charged with tension and determination as every lift holds enormous weight and responsibility. At the Petrobras yard in Rio Grande, the crew works with a PTC crane, one of the largest lifting machines in existence, to maneuver massive structures into exact position. The process begins with preparation. Ground teams secure rigging equipment, double-checking connections between slings, hooks, and the steel modules to be moved. Every bolt and link is inspected to ensure stability before the crane even starts its motion. This moment of inspection builds anticipation, as silence precedes the immense power of the lift. With everything secured, the PTC crane activates. Its counterweight system balances the enormous forces generated by modules weighing hundreds of tons. Load monitoring systems are engaged throughout the lift, continuously tracking stress on each sling and hook. Slowly, the structure rises from the ground, lifted steadily into the air. The gradual ascent creates a mix of suspense and admiration, as human planning combines with machine power. Operators maintain constant communication, ensuring that every movement follows a coordinated plan. Once suspended, the modules are shifted horizontally across the yard. The crane's reach and strength allow relocation over long distances, minimizing the need to move other equipment on site. Seeing such heavy steel glide through the sky is an unforgettable sight. Teams on the ground stand ready to guide the load into its final alignment. The next stage is positioning. Taglines keep the module steady while operators lower it into its designed location. Millimeter-level adjustments bring flanges and structural joints into contact. The intensity of this alignment shows how fragile even a massive object can feel at the final moment. Crew members monitor closely, tightening connections once the weight is fully transferred. The integration continues with multiple lifts repeated throughout the day. Each module, whether structural block, piping section, or equipment package, requires the same process of rigging, lifting, transporting, and positioning. Repetition does not lessen the impact. Every cycle demonstrates human focus and endurance. Coordination between crane operators, signalers, and ground teams ensures the project advances safely. By the day's end, the FPSO takes a more complete shape as modules join together. It's inspiring to see how determination and engineering converge on such a vast industrial scale. This sequence of heavy lifts illustrates not only the capabilities of Mammoet's equipment, but also the commitment of the people who operate it, shaping offshore energy production through strength and precision. Heavy steel components lie in position as the Geminis GHT-9 lathe prepares for machining. Its frame is built to handle the demands of long shafts and large diameters, giving operators the flexibility to tackle different workpieces. The cycle begins with the workpiece clamped securely between headstock and tailstock. Spindle rotation delivers stability while guiding the part through its first turning sequence. Tool posts slide smoothly along the bed, removing excess material and creating a uniform cylindrical profile. Milling capability is then activated, integrating additional functions without shifting the setup. A rotating cutter approaches the surface, opening the possibility for slots, flats, or complex geometries. This dual system combines turning and milling in one controlled environment. Coolant flows over the tools, reducing heat and maintaining cutting efficiency. Digital controls oversee feed rates and tool paths, ensuring each movement follows programmed instructions. The consistency achieved across repeated parts proves the machine's industrial value. By the end, a rough stock has become a precisely shaped component, ready for assembly or further finishing.
Sunrise Stainless operates large-scale stainless steel production in Mundra, Gujarat, India. The facility manages multiple production lines, including 11 tube mills for welded pipes and tubes. Operators monitor material feeding, welding, and shaping, ensuring each pipe meets ASTM and EN standards. Hard to imagine so many pipes being processed simultaneously. In the cold rolled coils section, coils are precisely rolled from 300 series stainless steel. Cold rolled coils are produced to meet ASM EA249, A269, A270A 312 specifications. The R&D team adjusts roller pressures and speeds for specific gauge thicknesses. Seeing rollers this size handle delicate stainless steel without damage is kind of satisfying. Automated systems measure coil thickness continuously, flagging deviations instantly. Quality checks include both surface inspection and mechanical property tests. QA staff perform random checks for surface defects, dimensions, and mechanical properties, keeping rejects minimal. Welded pipe production begins with pre-cut stainless steel strips, fed into tube mills where the edges are welded, forming tubes. The tubes range from 1/2 to 12 inches NB and SCH 10 and 40, mainly 300 series. Operators check seam quality constantly. Tubes then pass through sizing units and are straightened before packaging. Makes you wonder how many hands coordinate this huge workflow smoothly. Handrails and architectural stainless steel fittings are produced in a separate unit. Stainless steel sheets are cut, bent, and polished using specialized machines. Operators confirm angles, dimensions, and surface finish manually and via sensors. Quite neat to see precision combined with industrial force here. Five additional pipe mills were added, allowing over 7,000 tons extra production annually. Production schedules are adjusted to ensure timely delivery without compromising quality. All materials comply with ISO 9001-2008, ISO 14001-2004, and OSAS 18001-2007 standards. Sunrise Stainless supplies customers in USA, Europe, Turkey, and Brazil. The scale of
Steel production includes treatment. Ladles heated, molten poured, chemistry balanced, samples analyzed, then refined steel delivered forward for continuous casting. How does scrap metal transform into high-grade bars strong enough for engines and gearboxes? At Georg's Marine Hoot, the journey begins with recycled steel melted in an electric arc furnace, reducing emissions through advanced filtering. Alloying elements refine the molten metal, tailoring its strength and durability. Continuous casting shapes strands, while block casting prepares massive forgings. Rolling mills deliver accurate diameters, switching quickly between orders. Surface treatments polish material into bright steel. Each movement feels decisive. Transformation carries raw intensity. From solid square billets, countless steel bars are rolled into practical forms: round, square, and flat. Molten steel is cast into square billets, sorted by grade, and heated for rolling. Billets pass through rolling stands, forming rounds, squares, or flat bars while refining internal grain structure. Surface cracks are detected with Dr. Forster, Circoflux, and internal defects assessed by GE testing. Optional softening adjusts hardness and ductility. Finished products are cut, inspected, and prepared for shipment. The process combines thermal control, mechanical force, and quality oversight. In the heart of Pittsburgh, a renewed SBQ mill demonstrates higher efficiency and sharper bar standards after major upgrades. The energy in the facility is immediately noticeable as glowing billets move forward. A billet exits the furnace at nearly 100 degrees Celsius and passes descaling to prepare for shaping. The compact breakdown mill with a reversing stand reduces its cross-section, rotated by a grip-type tilter. Each rotation feels like a reset before the next powerful pass. Material then travels across an insulated roller table to preserve heat, entering 4 housingless stands in HV arrangement. Ends are cropped, and further shaping follows with short-space stands. The 3-roll PSM becomes the heart of the line, adjusting hydraulically under load for SBQ bars. Real-time control ensures remarkable stability. Cassettes can be swapped in under 5 minutes, aided by CCD calibration. This speed highlights efficiency in heavy industry. Downstream, a laser gauge performs 500 scans per second, feeding automatic control. Bars are cut to length, cooled on the bed, and bundled. Final products: heavy-duty chains for mining start as 8-meter steel bars, cut into precise 33-centimeter lengths. Only high-grade alloy steel is used, prepared to withstand extreme underground stress. The bars are heated by induction to nearly 600 degrees Celsius. Once glowing, the blanks are bent into rough loops, and sparks fly during welding. This flash removes surface impurities while sealing the joint without oxygen intrusion. Each welded piece weighs several kilograms, demanding strength and speed from workers handling hundreds per shift. Next, the links are pressed flat under powerful hydraulic equipment, shaping them into so-called flat links. These are combined with round links in a carousel system, gradually extending into continuous chain strands. 100 meters of chain weighs over 3.5 tons, and every segment must align perfectly. The sight is truly striking when glowing steel stretches link by link. Heat treatment follows. Chains are hardened at about 900 degrees Celsius, then quenched in water. This gives durability for years of service in demanding mines. Smaller chains are produced differently, with automated machines shaping and welding wire into closed loops in seconds. Every chain is tested under extreme tension. Loads exceeding 200 tons are applied until elongation is measured. Breaking below standard is unacceptable, but passing means the chain can be trusted underground. Finally, a protective coating bath seals each link, ensuring resistance against rust. Production concludes only when inspection confirms strength and reliability.
The global steel chain production industry is valued at over $5 billion and is expected to grow at a CAGR of 4 to 5%. China dominates production, accounting for over 50% of global output, followed by India, the US, and Germany. High-grade alloy steel is used for industrial chains, with tensile strengths ranging from 300 megapascals to over 1,000 megapascals. Major applications include automotive, 30%, construction, 25%, and heavy machinery, 20%.
The atmosphere shifts as heat and steel come together for a trial run, marking the very first attempt to forge these parts. Every stage carries expectation, where results depend on how metal reacts under fire and force. Long alloy bars are cut into equal segments, ensuring each will enter the furnace under the same conditions. Temperature probes constantly monitor the steel. Maintaining consistency for optimal forging. Induction heating quickly raises the temperature, softening the steel until its glow signals readiness. The billet's surface temperature is crucial, influencing malleability and grain structure. The glowing bars radiate energy, hinting at the precise control required for each stroke. A hydraulic press delivers crushing power, reshaping the billet into its rough geometry. Each die strike is calculated to refine shape while avoiding stress concentrations. Dies keep alignment, preventing distortion as strength is redistributed through the steel. The impact reverberates across the shop floor, a reminder of raw industrial energy. This production captures how hydraulic power shapes dish ends for heavy industry. The intensity inside the shop is undeniable. Each blank is positioned under the hydraulic press, where fluid power generates immense pressure. Controlled strokes bend the metal into a perfect dish end. It's striking how force and accuracy combine here. Excess material is trimmed, surfaces are smoothed, and inspection confirms that thickness and curvature meet demanding industrial requirements. Here the spotlight is on the Czech Republic's forging industry, where modern technology and traditional craft work side by side to produce parts of immense importance. Each sequence feels like a balance between raw power and refined control, giving the audience a sense of unstoppable momentum. The process begins with selecting steel billets of specific grades. Chemical composition is verified to meet strict standards for carbon, manganese, and microalloy content. These are heated in large furnaces until the core temperature reaches forging range, often above 200 degrees Celsius. Thermocouples continuously monitor temperature at multiple points inside each billet. The uniform heat distribution is crucial, ensuring the metal remains workable without losing structural strength. Surface scale is removed to prevent defects during forming. The glowing orange bars make a strong impression, highlighting the transformation about to unfold. Once heated, the billets are transported to forging presses or hammers. Hydraulic and mechanical systems deliver thousands of tons of force, compressing the material into the desired shape. The press force is dynamically adjusted based on billet size and target geometry. Dies guide the deformation, creating forms ranging from simple shafts to complex automotive and aerospace components. It is striking how steel resists, yet ultimately yields under repeated blows. After forging, excess flash is trimmed away, leaving a more defined product. Trimming dies are machined to maintain tolerances within plus or minus 0.5 millimeters. This step is critical because the flash, although thin, can alter the overall geometry. Trimming presses ensure clean outlines, allowing the piece to advance into subsequent processing. Forged parts are marked with heat codes and batch numbers for traceability. At this stage, the rhythm of the workshop is intense, with presses and shears moving in rapid succession. Heat treatment follows, where controlled cycles of heating and cooling adjust hardness, toughness, and internal structure. Quenching tanks, furnaces, and tempering units ensure that each part meets mechanical requirements demanded by industries such as rail, automotive, and energy. Cooling rates are calibrated to prevent warping or residual stress. One can sense the importance of precision here, as even minor variations would compromise safety and performance. Machining further refines the components. Lathes, milling machines, and CNC centers bring dimensions within tight tolerances. Boreholes are drilled, surfaces are smoothed, and threads are added if required. Forgings emerge not only strong but also ready for exact assembly. Final diameters and concentricity are verified using coordinate measuring machines. The transition from rough block to finished part is truly fascinating, revealing the harmony of force and technique. Inspection is the final safeguard. Non-destructive testing, ultrasonic scanning, and dimensional checks confirm quality. Surface treatments or coatings may also be applied, extending durability. When accepted, the forged parts are shipped to clients in rail, automotive, construction, and power generation sectors. By this point, the entire journey feels like proof of both industrial power and skilled craftsmanship. Altogether, the forging sector in the Czech Republic demonstrates not only technical ability, but also resilience in adapting to new demands. Modernization, automation, and sustainable practices are integrated into a trade that has endured for centuries. Special alloy steel is also forged for aerospace applications, highlighting versatility. It is inspiring to see how heritage continues to evolve, delivering essential components for the future. Steel pipes take shape through hot Mannesmann rolling, forming seamless tubes for construction projects in Brno and Prague. The Scott Forge bar mill produces tartan bars with forged sound centers, planished surfaces, and exact dimensions, ready for machining or heat treatment. The workshop buzzes with energy as bars move through cutting, straightening, and testing stages. The rod, still warm, passes through guiding rollers that control tension. Hydraulic coilers bend it into precise spirals, forming large diameter springs. Operators monitor the alignment and pitch, ensuring uniformity. Temperature sensors continuously track rod heat to maintain optimal malleability. After coiling, each spring undergoes dimensional verification and stress testing, confirming durability for heavy-duty applications. The combination of heat, force, and technical oversight results in springs that are both robust and consistent. It's impressive to observe the balance between automated machinery and skilled human supervision at every stage. Every bell begins its journey with a vision, long before it echoes across the Alps. In the Glockengesserei Gusset workshop in Utendorf, Switzerland, artisans start by designing a Glock-style Swiss cowbell. The first step involves preparing the mold, compressing layers of fine sand and clay to ensure it holds every intricate detail. Craftsmen measure and layer the sand with precision to maintain consistent density. Special tools are used to press the sand uniformly, avoiding weak spots that could crack during casting. The mold is firmly pressed together to withstand the molten metal. Then craftsmen carefully carve letters and decorative patterns onto the mold, adding character and history to each bell. Sometimes additional impressions are added to enhance visual appeal. Next, bronze is heated in a furnace until it glows a vivid orange. Thermometers and visual cues help determine the precise pouring temperature. Artisans often swirl the bronze gently before pouring to achieve uniform consistency. The molten bronze is then poured slowly into the carefully pressed mold. After cooling, the mold is broken away to reveal the rough bell. Hearing the bell's first clear note is an exhilarating moment. What seems like a single strike of bronze is in truth the result of weeks of labor, as clay molds, wax ornaments, and fire come together in silence. The weight of tradition feels tangible here, carried in every brick and layer of earth. The work opens with creating the base block. Around a welded frame, refractory bricks are laid and bonded with clay, then coated with ash to prevent fusion with the core. This stage sets the ground for everything that follows. Even the smallest action here feels tied to centuries of practice. Next comes the core, formed from clay mixed with horse manure and fibers for strength. Layer after layer dries on a heated stand. reinforced by a template that encodes weight and pitch. It is astonishing to realize that sound itself is hidden in these outlines before any metal is poured. Once hardened, the core is isolated with ash, preparing it for further building. The quiet discipline of this part reminds one that endurance shapes music as much as talent. The false bell takes shape next. Clay layers are smoothed with the rotating template, producing a temporary replica. Hot beef tallow coats the surface, creating a base for decoration. At this point, artistry becomes visible. Letters, ornaments, and figures in wax are applied by hand. These adornments define not only the look, but also the identity of the bell. It seems that identity etched into clay before bronze gives it permanence. Craftsmanship here is more than technique, it is an act of cultural memory. The cope is then added. Multiple clay coats, strengthened with wire, are applied over the decorated false bell. Heat drives out wax and fat, leaving perfect impressions inside. The crown is modeled separately and later joined to the cope. Casting follows. The mold is buried in earth and connected with channels for molten metal. Inside the furnace, bell bronze, 78% copper, and 22% tin, melts between 1140 and 1200 degrees Celsius. When tapped, glowing metal streams into the molds, replacing the lost wax bell. The largest molds are filled first to secure the most important pieces. Cooling spans days, ensuring integrity. There is a stillness during cooling that contrasts deeply with the earlier fire and noise. Once unearthed, the raw bell undergoes cleaning. Runners are cut away, surfaces ground, and ornaments sharpened. The crown is drilled for the clapper, which equals about 4% of the bell's mass. Every strike of a tool here feels like unveiling hidden character from within the bronze. Tuning forms the final stage. Using tuning forks or digital devices, craftsmen adjust thickness until the harmonics align. The bell is polished, engraved with decorative details, lacquered, and prepared for delivery. Before departure, it is struck 3 times without a clapper, an echo marking both farewell and beginning. To witness a bell completed is to understand how patience, material, and devotion can merge into enduring sound. The path to a bell's powerful tone begins in a quiet foundry, where raw materials are transformed step by step into lasting sound. The making of the 25-ton bell for the cathedral in Bucharest reflects not only the strength of metal, but also the endurance of human skill. Even in silence, the space feels charged with anticipation, as though history itself is waiting to be cast. Its journey began almost a year ago when a family, practicing bell casting for 14 generations, received the order for this monumental creation. The weight of history is felt in the quiet murmur of the foundry, as over 4,000 hours of labor are already behind this bell. Traditional techniques guide the decorative process, yet advanced software developed in collaboration with universities ensures that each curve and rib is mathematically perfect. 3D modeling simulations predict how the bell will vibrate and resonate. It took 15 years to develop this system, allowing now for flawless execution in bells of varying weights and sizes. The bell's tone mirrors the famous Boomerang in Vienna's Stevensdom, but is amplified by 5 extra tons of bronze, producing a sound of remarkable depth and resonance. The mold making begins with a brick core, covered with layers of clay to form the inner cavity. Each layer is smoothed and compressed with care, ensuring stability. From this, the false bell is shaped, a sand and clay replica matching the final bell's exterior. The wax impressions are carefully prepared to capture the intricate details of inscriptions and decorative elements. Malleable wax is poured or brushed over the coated mold, carefully filling every carved groove and curve. Each pour of wax seems delicate yet decisive, forming an ephemeral sculpture. Building the false bell is a slow, exacting process. Clay is pulled up layer by layer and secured with tensioned wires. Sometimes, layers slip unexpectedly, creating gaps that cost hours to repair. The team must carefully readjust each layer, maintaining even pressure across the surface to prevent further mishaps. All hands in the workshop contribute to building the 5.5-ton false bell. Mistakes become lessons, shaping both the bell and the artisans. Once the wax impressions for inscriptions and portraits are carefully placed, the outer clay mantle is applied in multiple layers, including a secretive fine clay mixture enhanced over generations. The mantle is allowed to dry slowly to prevent cracks. Next comes the thorough pouring of over 30 tons of bronze, heated to 100 degrees Celsius and transferred using thermally insulated containers. The bronze is carefully maintained at target temperature, with Holtz cola used to sustain heat during long transfer periods. Thermocouples monitor the metal continuously, and each 10-kilogram bar is loaded individually, 1,000 bars for a single large melt. Goosebecker and Steiger channels are installed, directing the molten metal through ceramic pathways while maintaining controlled pressure and avoiding cracks. Pouring sequences follow a strict timing protocol. The flow is carefully directed through ceramic channels into the mold, gradually filling the cavity. Moments of tension peak as the molten metal courses through the channels, and every participant holds their breath. Flow rates are calculated to minimize turbulence and prevent air pockets. Time seems suspended, every second stretching endlessly. After the initial pour, additional bronze is added to ensure the bell is fully solid and free of voids, guaranteeing the perfect tone. Ultrasonic tests are later performed to detect any internal flaws. The team watches closely, eyes reflecting the molten gold within. Precision molds and guided channels ensure the bronze spreads evenly. Once cooled, the mold is carefully dismantled. Mechanical and hand tools are used to avoid damaging the bell surface. The bell emerges, glistening like a golden star, the culmination of months of labor and expertise. Cleaning and detailed inspection follow, especially for the delicate decorative elements. Laser scanners are employed to verify exact dimensions. Even the bell clapper undergoes extensive work. A 700-kilogram steel cylinder is forged, shaped, heat-treated, and refined to produce a perfect strike. Dynamic testing ensures each strike produces the intended C0 tone. Its design balances weight and geometry, ensuring centuries of reliable performance while preserving the bell's tonal integrity. The final assembly is checked for alignment and impact angle. With the clapper installed, the family's task concludes, leaving only transport and installation. In the quiet of the foundry, relief and satisfaction mingle with pride, a moment reflecting both art and human perseverance.
A large steel beam waits as the hydraulic bending machine activates, ready to transform raw metal into precise curves. The sheer scale and energy of the PRO 100 in action immediately captures attention. The PRO 100 demonstrates impressive force, capable of bending thick metal profiles with controlled pressure. Operators observe each adjustment closely, admiring the smooth motion and robust performance of the machine. Each movement is calculated, ensuring every bend aligns perfectly with engineering expectations. The first step involves feeding the profile into the rollers, aligning it precisely with the bending axis. The tension is monitored constantly to prevent overstressing the steel. As the rollers engage, the machine begins bending the profile along the predetermined curvature. The hydraulic system maintains steady pressure, ensuring uniform deformation across the length. It's striking to see how consistent the bend remains, even with profiles of substantial size. Technicians can adjust the bending angle in real time, tailoring the curve to exact specifications. This combination of strength and adaptability allows the machine to handle various steel sections efficiently. The machine's programmable control unit records bending sequences for reproducibility and quality assurance. The efficiency and precision of the PRO 100 make it a remarkable tool for modern metalworking, blending raw power with controlled versatility. This display of engineering excellence highlights how advanced machinery reshapes metal into functional, complex forms without compromising structural integrity. Once the initial bend is achieved, the profile is carefully repositioned to execute secondary curves if required. Watching the profile gradually take its final shape evokes admiration for both engineering and human skill. Sensors and controls track the process, providing feedback on force, angle, and roll position. The synergy between operator insight and hydraulic control ensures high-quality results every time. Finally, the profile exits the machine, revealing a cleanly bent section ready for use in construction or industrial projects.